Alright, so in this video, I'm going to be explaining another important article on graph representation learning with the title Drop Message Unifying Random Dropping for Graph Neural Networks. So, this important paper in 2023. Graph neural networks are a powerful tool for graph representation learning. Despite their rapid development, GNN also faced some challenges such as overfitting, oversmoothing, non-robustness, oversquashing, and many other things. Previous works indicate that these problems can be alleviated by random dropping methods, which integrate augmented data into models by randomly masking parts of the input. However, some open problems of random dropping and GNNs remain to be solved. First, it is challenging to find a universal method that are suitable for all cases considering the divergence of different datasets and models. Second, augmented data introduced to GNNs cause the incomplete coverage of parameters and unstable training process. Third, there is no theoretical analysis of the effectiveness of random dropping methods in GNNs. So we propose a novel random dropping method called dropmessage, which performs dropping operations directly on the propagated messages during the message passing process. Most importantly, we find that dropmessage provides a unified framework for most existing random dropping methods, based on which we give theoretical analysis of their effectiveness. Furthermore, we elaborate the superiority of dropmessage. It stabilizes the training process by reducing sample variance. It keeps information diversity from the perspective of information theory, enabling it become a theoretical upper bound of other methods. To evaluate our proposed method, we conduct experiments that aims for multiple tasks on 5 public datasets and 2 industrial datasets with various backbone models. So we propose a novel random dropping method called dropmessage for all message passing GNNs. Existing random dropping methods can be unified into our framework via performing masking in accordance with certain rule on the message matrix. In other words, those methods just can be regarded as just one special form of drop message. And then we theoretically demonstrate the effectiveness of the random dropping methods, filling the gap in this field. Also, it can alleviate better this overfitting, oversmoothing, and non-robustness. Compared to other methods, this drop message is a unification of drop edge, drop node, many variants of dropping by just masking so this drop message, because it is generalization of previous approaches, it's very important to focus on this, why we can do this. So this is an illustration of drop message and other existing random dropping methods. Considering the message propagated by the center node 1, drop message allows to propagate distinct messages to different neighbor nodes. Of course, this kind of I have seen this kind of idea in other articles, but this is explicitly written, and the focus of this paper is only on this. So you can unify many articles like drop node, drop edge, drop out. Unify all of these ideas into drop message. So for M12, we have this row. For M13, we have this representation. Similarly, so this is the dropped one, but the blue one is the message vector. So we call it drop message because one entry of that is dropped. That is very interesting. I think it can only be used for, it can also be used, of course, for over squashing, but the authors didn't mention that. Of course, it's very complicated to prove that you are not changing the topology of the graph by this kind of explicit representations of messages. So, message passing, aggregate, and then update to get next layer. So, from the perspective of message passing, we can gather all propagated messages into a matrix M. So specifically, each row of the message matrix corresponds to a message propagated on a directed edge. And so phi is mapping that generates the messages. So the approach is very easy, it's so easy that it's just different from existing random dropping methods. Drop message performs directly on the message matrix M instead of the feature matrix or the adjacency matrix. More specifically, drop message conducts dropping on the message matrix with dropping rate, which means that delta of cardinality of your M matrix elements of the message matrix will be masked in expectation. Formally, this operation can be regarded as a sampling process. For each element in the message matrix, we generate the independent mask epsilon I from this Bernoulli of 1 minus delta. So then we obtain the perturbed message matrix M tilde by multiplying each element with its mask. Finally, we scale M tilde with the factor to guarantee that perturbed message matrix is equal to original message matrix in expectation. Thus, the whole process can be expressed like this. So we do not need to generate complete message matrix explicitly because each row in the message matrix represents a distinct directed edge in the graph. And our proposed drop message can be applied to every directed edge independently. This property allows drop message to be easily parallelized, for example, edgewise, node-wise, batch-wise, and to be applied to the message passing backbone model without increasing time or space complexity. So this lemma is the core of this paper. Drop out, drop edge, drop node, and drop message perform random masking on the message matrices in accordance with certain rules. So when performing random dropping on graphs, we use perturb matrix m tilde instead of original message matrix. Thus, the objective function expectation can be written like this. So there are some advantages of drop message, like reducing sample variance. All random dropping methods are challenged by problem of unstable training process, if you remember. As the existing work suggests, it is caused by the random noises introduced into each training epoch. These noises then add the difficulty of parameter coverage and the instability of training process. Generally, sample variance can be used to measure the degree of stability. The input of each training epoch can be regarded as a random sample of the whole graph. And the sample variance is calculated by the average difference of every two independent samples. Compared with other random dropping methods, drop message effectively alleviates the aforementioned problem by reducing the sample variance. And the theorem 2 justifies that. So drop message presents the smallest sample variance among existing random dropping methods on message passing GNNs with the same dropping rate delta. Drop message can keep information diversity in expectation. Delta is dropping rate. And the data sets are very popular. These CiteSeer, PubMed, Quora. So for different tasks like node classification, link prediction, for link prediction we usually use Quora, PubMed, these datasets, CiteSeer. And for different models, for example, I've explained graph attention, graph convolutional networks. APPMP is very popular. So this one, if you look at the PubMed, is 95%. Of course, the highest one is in bold. For example, 96 for PubMed using drop message. So this drop message is more significant, maybe 1%, less than 1% significant than the original one. And of course, they could also work on graph classification. But they focused on this over smoothing. And you see, as the number of layers grows, first the accuracy improves, then the trend goes down. It's like stock market, goes resting and then increase, resting. But you know, it goes down for a reason. And of course, this is a test accuracy. For a good measure of over smoothing, like previous videos, I said mad gap is important. Mad gap. Another one, Dirichlet energy, if you remember.